Every slope we have measured so far handed back a different function. Squaring became doubling. Sine became cosine. Nothing has ever come back as itself. So here is a fair question. Is there a curve whose steepness at every point is exactly its own height there? Start with doubling. 2 to the power of x, it does at least grow in proportion to how big it already is. At the start, its height is 1. So if this is the curve we want, its slope at the start has to be 1 as well. Measure it. Step 1/10 gives 0.718, 100th 0.696, 1000th 0.6934. The readings settle onto 0.693. Height 1, slope 0.693. This curve is too flat. So try tripling instead. 3 to the power of x. The same measurement at the start gives 1.099. Now it is too steep. 2 flat at 2, 2 steep at 3. Somewhere between them sits a base that gets this exactly right. That base is what this lesson hunts. And when we corner it, the number will not be one that we chose. It will be the answer to the question. Before hunting, one piece of structure. It turns a search for a curve into a search for a number. Take any base at all, and push x forward by a small step. The new height is the old height, times the base raised to the step. That is the index law and nothing more. So the gain in height is the old height, times the base to the step, minus 1. Divide by the step to make it a rate, and then look hard at what is left in the bracket. There is no x in it. That bracket is decided by the base alone. So the slope of an exponential is always its own height, multiplied by one fixed number that belongs to the base. Which means the slope curve of any exponential is a copy of the curve itself, scaled up or down. Here is doubling, and here is its slope curve. Same shape, squashed to 0.693 of the height. And here is tripling, with its slope curve standing above it at 1.099. So we are not looking for a new shape. We are looking for the base whose one number is exactly 1. Call that number the growth factor of the base. 2 gives 0.693, 3 gives 1.099. It rises as the base rises, and it never jumps, so it passes through 1 exactly once. So squeeze it. Halfway between 2.5 gives 0.916, still short. 2.75 gives 1.012, just over. 2.7 gives 0.993. 2.72 gives 1.0006. 2.718 gives 0.9999. The base is cornered. 2.71828, and the digits carry on. This number is called E. It was not measured in nature, and it was not chosen because it is tidy. It is the base whose growth factor is 1. That is a definition by a property, so it is worth saying why it is allowed. The growth factor climbs smoothly from below 1 to above 1, so exactly one base can be sitting at 1. And that is the whole content of this number. Not a decimal to memorize, the answer to one question about slopes. So write the curve with that base, e to the power of x. Its slope is its height times 1. Its slope is its height. Draw the curve, then draw its slope curve on the same axes. There is only one curve on the page. At the start, height 1 and slope 1. One step along, height 2.718 and slope 2.718. 2 along, both are 7.389. Check the definition straight off the numbers. Step 1000th gives 1.0005. It is climbing onto 1. Now here is that fact as geometry, and it is the prettiest thing in this lesson. Draw the tangent anywhere on this curve. Follow it down to the axis. It lands exactly 1 unit to the left of the point you started from, every time at every height. That fixed distance is the signature of the curve. Steepness in exact proportion to height everywhere. One more thing, stated here rather than proved. Nothing else does this. Any quantity whose rate of change equals its own size follows this curve, up to a constant multiple. That is why this number turns up wherever growth feeds on itself. There is a second way people meet this number, and it looks completely unrelated. Money, 1 unit, at 100% interest for a year, but paid in installments. 2 installments of a half give 2.25. 12 monthly installments give 2.613. Daily gives 2.7146. A million installments give 2.71828. That is our number again, and it deserves an explanation rather than a raised eyebrow. Our base was pinned by one property. Raised to a small step, it comes out as 1 plus that step, very nearly. So turn that sentence around. The base is 1 plus the step, raised to 1 over the step. Now write the step as 1 over a whole number. That is the installment formula, exactly. So these are not two facts. The installment ladder and the slope hunt are one question, asked from opposite ends. Two quick runs, because in an exam what you need is speed. The derivative of e to the power of 3x, a function tucked inside another, so that is the chain rule from lesson 7. Outer rate e the power of 3xx, inner rate 3, giving 3e the power of 3x. Now x times e to the power of x, two things multiplied, so the product rule from lesson 8. 1 times the power of xx plus xx the power of x. And now, we can settle the number from the start of this video. Doubling is our own base, raised to x times 0.693. So its slope is 0.693 times itself, which is the reading we measured in the first minute. That number has a name. It is the natural logarithm of 2, and where logarithms come from is exactly the next lesson. Two traps. First, e to the power of x is not x to the power of e. One has the variable upstairs, and the other has it downstairs, and they behave nothing alike. Second, the power rule does not reach a moving exponent. 3 to the power of x does not become x times 3 to the power of x minus 1. There the base is fixed, and the exponent moves, which is the opposite arrangement. We did not find a number and then hunt for a use. We asked whether a slope could equal a height, and this number was the answer. One question, one curve, its own derivative.